In this video, we're going to look at the examples using simple theory of torsion on pages 49 and 50 of the course notes. On the screen just now is example 1, and in this question we're asked to find three things: the torque carried by the shaft, the maximum shear stress in the shaft, and the angle of twist in the shaft between the motor and the machine in degrees. And that last part is important, and we'll need to remember a conversion in there because our formula is going to give us our answer in radians when we get to that point in the question. So let's start off with part 1 of the question. We're asked to find the torque. Now, torque can be found in two ways in this part of the course. We can use our torsion equation, or we can use the equation for power. And it's going to be the equation for power we use here. If we tried to write out the torsion equation, we'd find we just did not have enough information from the question. So the formula we're going to need is this one here. Power is equal to torque times angular velocity. And we have two of these three things in the question. We're told that the power of the motor is 11 kilowatts, which is the same as 11,000 watts. And we're told that the angular velocity is 350 RPM, which we'll convert into radians per second, because that's the unit we need for this formula. And to convert RPM into radians per second, we take 2 pi multiplied by the angular velocity in RPM and divide that by 60, and that converts revolutions per minute into radians per second. And when we work that out, we find that we have a value of 36.65, so 2 decimal places, radians per second. So we now have all the information we need to find our torque. So we'll rearrange our formula to get torque is equal to power divided by angular velocity, and put in these two values that we've taken from the question and converted to the appropriate units for this formula. So 11,000 divided by 36.65. This gives us an answer of 300.1 Newton meters. That's rounded to 1 decimal place. So that's part 1 of the question. In part 2 of the question, we're asked to find the maximum shear stress in the shaft. And it's important to remember maximum shear stress occurs at the outer edge of the shaft. So the radius of the shaft, at that value of the radius, that's where the maximum stress will occur. So let's have a look at question 2 now, and we'll have a look at what information we have. Well, this is where it's worth writing out the torsion equation. So we know that torque divided by polar second moment is equal to shear stress divided by radius is equal to the modulus of rigidity times the angle of deflection or angle of twist divided by the length of the shaft. And when we're doing a problem like this, we're going to use two of these three parts of the question. So we don't need to know everything, we need to know just enough in order to work things out. Now what we're looking to find is the torque. We're looking to find torque. This is a wee question mark here, that's what we're looking to find. We've just calculated, that's not maximum stress we're looking to find, that's tau. Tau maximum stress, that's what we're looking to find. Torque we found in the first part of the question. Radius we can take quite easily from the value of the diameter of the shaft. And polar second moment of area, well, we haven't been given that, but it's something we can find. So we can use these two ratios on the first and second fractions, if you like, to find our value for maximum shear stress. Well, maximum shear stress occurs at maximum distance from the center of the shaft. So that is our radius. So our diameter is equal to 30 millimeters, which is equal to 0.03 meters. And so our radius is going to be equal to half of that, 0.03 divided by 2. So it's going to be equal to 0.015 meters. So we have the radius. We have the torque from the first part of the question. So all we need to do is to find the polar second moment, And we'll do that just now using the formula given to us in the course notes for polar second moment of a solid shaft, because that is what this is in this question. And that's given by J is equal to pi times the diameter to the power of 4 divided by 32. And we do this using diameter in meters for this part of the course. We're always, for our torsion questions, we're going to be using meters for our units. It doesn't actually matter. We could use, if we wanted to, millimeters for everything, but our numbers are going to turn out nicer if we keep everything in meters. So that's what we'll do here. And working at that, we have pi times 0.03 to the power of 4 divided by 32. And putting that into your calculator, you should get a value of 7.952 times 10 to the minus 8. And remember, our units for polar second moment are meters to the power of 4. So we have values for J, T, and R as we did. So let's write out our formula again with just the parts we need and rearrange to find tau. And specifically, and you'll see this if you look at this example in the course notes, we're going to refer to tau as tau max and R as R max, because the radius of the shaft is the furthest possible point from the center. So we have T over J will give us tau max divided by R max. It is only tau max because we are at the maximum distance, the radius from the center. So rearranging, we're going to get tau max is equal to torque times R max, our radius, divided by our polar second moment. And putting this in, we're going to have 300.1 times 0.015 divided by the value we've just worked out for polar second moment, which is 7.952 times 10 to the minus 8. If we enter all of that into our calculators, what will come out is 5.661 times 10 to the 7 newtons per meter squared. And you can see, if you look at the course note example, they have chosen to represent this as 56.61 times 10 to the 6 newtons per meter squared. These two are the same thing. We can shift that decimal point to the right and reduce our exponent by 1. The reason for selecting this is because times 10 to the 6 is a million, and that allows us to switch from newtons to meganewtons. So we can write 56.61 meganewtons per meter squared. Now, unless you're asked for these units specifically in a question, there would be no reason to take this any further than the original answer of 5.661 times 10 to the 7 newtons per meter squared. The other steps are just a matter of tidiness. So if we go back to our original question, we can see that we have answered questions 1 and 2, but we still have question 3 to consider. So let's look to how we're going to find the angle of twist. But we can again use our torsion formula. T over J is equal to tau over R equal to G theta over L. Now we have now worked out every quantity in this formula apart from theta, so we just need to choose 2 of these fractions to use for this last calculation, and we're going to choose T over J is equal to G theta over L. Now it would be entirely possible to calculate this with tau over R equal to G theta over L, and if you've done part 2 correctly, then you get the correct answer here as well. The reason for not choosing that is simply a matter of caution. Our value for tau depends on our values from T and J, so we've had to do more rounding to get there, and potentially we could have made a mistake if this was a real live problem under exam conditions. So it's safer to pick T over J equal to G theta over L, and potentially preserves more accuracy in the answer as well. We already know T and J, we found these previously. In the question, we are given values for G and L as well. We're told that G is equal to 83 giganewtons per meter squared, and that is the same as 83 times 10 to the 9 newtons per meter squared. We're going to solve this question using newtons as our unit of force and meters as our unit of length. And the length of the shaft is 2 meters. We're given that in the question also. But we can remind ourselves what we got for other values. For torque, we found that was 300.1 Newton meters, and our value for J polar second moment, we worked that out previously as well, and the value we obtained for that was 7.952 times 10 to the minus 8 meters to the power 4. So we have the 4 values we need. So we'll rearrange this formula first of all to get theta is equal to TL over JG, and this results from dividing both sides by G and multiplying both sides by L. You'll be able to solve the problem by substituting all the numbers in the previous line and then rearranging, but sometimes it can be a lot neater to get our variables sorted out first of all and then put the numbers in, as we're doing here. And putting in our values, we'll have 300.1 times 2 divided by 7.952 times 10 to the minus 8 times 83 times 10 to the 9. So be careful with all of these exponents when entering this into a calculator. If you've done all this correctly, you'll get 0.09094 to 5 decimal places there, and that's in radians. But remember, the last thing was the question asked us to give our answer in degrees. So we will say that theta is equal to 0.09094 multiplied by 360 divided by 2 pi, because in one circle we have 360 degrees, and in one circle we have 2 pi radians. So to convert radians to degrees, we're dividing by 2 pi and multiplying by 360. And the answer we get to 2 decimal places is 5.21 degrees. So we have met all of the criteria for this question. We've answered all the questions, and we've worked through using the different formulas from torsion theory, the torsion equation itself, and along the way, the formula for polar second moment and our formula for power involving torque and angular velocity. So the main thing in this question is using the formulas correctly and making sure we do our unit conversion. We'll continue now on to look at example 2. This is in the following page, page 50 of the course notes. So example 2, there's a couple of differences which should be immediately apparent with this question. And the most important thing to note is that we're dealing with a hollow cylinder. So when it comes to any calculations for polar second moment, what we want to do is use the hollow shaft formula for polar second moment of area, not the solid shaft formula, and that will be based on the 2 diameters that were given in this question. So let's think about what we're being asked here. We are being asked to find the maximum shear stress. So the maximum shear stress we know occurs at the point furthest from the center, so it occurs on the radius. I'll indicate on the diagram, little red dot, maximum shear stress occurs here. Indicated there. So the point we've been told about, point A, is not where maximum shear stress occurs, but it is the shear stress at that point, and that is something that we can use in our formula to find the shear stress at the edge, so the maximum shear stress. So let's have a look at what's going on here. Well, first of all, we're going to need to find out what the torque and the polar second moment of area are. And the reason we know we need to find these is because we can find polar second moment of area from the shape of the shaft, because we have enough information about its dimensions. And we know we're not going to be using anything to do with modulus of rigidity or angle of twist or length of shaft. We're just not given any information like this. So the part of the torsion formula we're going to be relying on in this example is going to be T over J is equal to tau over R. Now, our torque and our polar second moment of area will be the same at point A and at the edge of the cylinder as well. So we're going to use these in order to find what the stress is at the outside of the cylinder. We'll start off by finding J and T. Well, in order to find J, we'll be using the polar second moment of area formula for a hollow shaft, which is J is equal to pi times the outer diameter to the power 4 minus the inner diameter to the power 4, all divided by 32. But what are these diameters? Well, capital D, we're told, is 30 millimeters, but we're going to be working in meters here. So that's going to be 0.03 meters. And lowercase d is our inner diameter, which is 20 millimeters. And again, we're working in meters, this will be 0.02 meters. So we have our two values for capital D and lowercase d. We can put these into the formula for polar second moment of area and calculate it. 0.03 to the 4 minus 0.02 to the 4 times pi, all divided by 32, gives us a value of 6.381 times 10 to the power minus 8 meters to the power 4. And we now have enough information to calculate the torque using the part of the torsion formula we've selected. And how do we do that? Well, we can say torque over polar second of area is going to be equal to the shear stress at point A divided by the radius at point A, because we have this information. We've just worked out polar second moment of area. We're given the shear stress at point A in the question. Just looking up there, we can see that tau at point A is equal to 20 meganewtons per meter squared, which is the same as 20 times 10 to the 6 newtons per meter squared. And that occurs at the radius of the inner part of the shaft. And so that's equal to half the inner diameter. So the radius at A is going to be equal to lowercase d divided by 2. And we know it's 0.02 meters divided by 2, so 0.01 meters. So we have 4 variables in our question and 3 pieces of information, so we can find torque. So torque will be equal to polar second moment of area times the shear stress at A divided by the radius to get to A. And that's equal to 6.381 times 10 to the minus 8 multiplied by our shear stress at A, which has been converted from meganewtons per meter squared into newtons per meter squared. So that's 20 times 10 to the 6. And that's all divided through by our radius out to point A, which is 0.01. Putting all of that into our calculator should yield an answer to one decimal place of 127.6 Newton meters. So we now have our torque. Now this is where we can use something, it's quite a clever trick in this question. Because torque and polar second moment of area do not vary with our distance from the centre of the cross section of the shaft, we can also write that torque over polar second moment of area is equal to the maximum stress divided by the maximum radius. And of course, the maximum radius is just the outer edge of the shaft, specifically the distance from the centre of the cross section to the outer edge of the shaft. So our max value is going to be given by the capital D divided by 2, so 0.03 divided by 2, which gives us 0.015 meters. And the value for tau max is what we're trying to find. And the values for torque and polar second moment we've calculated in the previous steps. So to find tau max, we're going to have our torque multiplied by the radius from the centre of our shaft to the outer edge, divided by polar second moment of area. And putting in these values, we can see the torque that we worked out in the previous step, 127.6. The R max we found is 0.015, and our polar second moment of area we've previously calculated that is 6.381 times 10 to the minus 8. Putting all of this into the calculator yields an answer to certainly 3 decimal places after the decimal point here, 3 times 10 to the 7. That would be 3.000, but 3 times 10 to the 7 newtons per meter squared, which can also be written as 30 times 10 to the 6 newtons per meter squared, or indeed 30 meganewtons per meter squared. 30 times 10 to the 6 is 30 million. 30 million newtons is 30 meganewtons. But as in the previous example, had you given your answer 3 times 10 to the 7 newtons per meter squared, the question doesn't ask us to convert to meganewtons. You'd have been perfectly correct to leave your answer as that. One final observation in this problem, which is if you observe these two equations here, T over J is equal to tau A over RA, and T over J is equal to tau max over R max, we could have actually saved ourselves the need to calculate torque or polar second moment of area by simply saying that tau A over RA is equal to tau max over R max. This is true because the strain, that's how much deflection is taking place, is proportionate to the distance from the centre, and the stress is proportionate to the strain. So effectively, if we double our distance from the centre, we would be doubling our shear stress experienced at that point, and we can go up by any proportion. So we could have saved ourselves a couple of steps there, but that's not the sort of connection you'd be required to make in an assessment style question, but it would be quite correct to do so, and if you spotted that shortcut, you'd still be able to get the marks that way as well. So just a little thing to think about, but not included in the course notes. But that concludes the two examples, and you might want to then go through these now with the video to see the steps explained in detail as you read through it.